Good morning, ladies and gentlemen. Good morning, Mr. Chairman. I am pleased to be here to present our recent results concerning energy autonomous localization and tracking. I am Alessandra Costanzo from the University of Bologna in Italy, and I would like to acknowledge the work of my colleague Nicolo Decarli, Davide, Dardari, and Diego Masotti. In my presentation, I will briefly discuss the motivation of this work and the new ideas about next generation RFID tags based on UHF channel for energy harvesting and the ultra UWB channel for communication and localization. And I will describe our new system concepts that is based to derive the UWB signal by exploiting higher intermodulation products by scattered by the tag. And I will show how these results can be exploited by a signal processing technique in order to perform localization strategy, and I will show some measurement results. It is well known that the centimeter level localization and tracking with passive tag exploiting energy harvesting could enable new interesting applications, such as in the field of baggage sorting, crowded RFID scenarios, and recently my group has developed an ESE project called LOST that has been able to demonstrate real-time tagging of objects inside the International Space Station. Usually there are three main methods to perform localization using standard UHF that are the one based on the RSSI of the signal, but it has the drawback of scarce accuracy. A better solution is based on the phase difference, such as the one used by FMCW method with an accuracy of about 20 to 30 centimeters, and the angle of arrival estimation with the same accuracy. All these solutions, even though they can obtain good accuracy, they are limited by the dimension, for example, of the antennas in the case of AOA, or the controlled conditions of the channel. We wanted to try to show a new possibility to get high accuracy localization by using ultra wideband signaling, and to really do so by means of an energy autonomous solutions, that requires lowering tag energy consumption and energy harvesting techniques. The idea is to exploit the concept of harmonic tag, in which the higher harmonic generated, for example, by the rectifier, can be collected instead of filtered out. But up to now, there has not been satisfactory solutions needed because of the need for dedicated circuitry, and usually they don't rely on UWB technology. Some examples of my group are shown here, where there are some attempts of combining UHF and UWB RFID tag with, on the left side, by exploiting an onboard UWB pulse generator. On the right side, by combining in a one-port antenna both frequencies, the UHF and the UWB. The solution I am describing here is quite different, since it is based on the exploitation of a standard rectifier for energy harvesting purposes that is excited by a multi-sign in the UHF band, and its output is partially used to store electric energy, and the rest is used to generate in a completely passive way a quasi ultra wideband signal to be backscattered by the same tag. So this is the main idea, to exploit multi-sign, not only to enhance energy harvesting capabilities, but also to being able to obtain a quasi ultra wideband signal. The rectifier is quite a standard one, except for the fact that it is equipped by means of two antennas. At its input, an UHF antenna is is used. At its output, a UWB antenna is used and is decoupled from the DC path. So the system is a standard rectifier and except for a suitable designed UWB system. So, for example, we have considered the situation of 4 multi-tone excitation of the rectifier spaced by 1 megahertz, and we have considered the maximum order of intermodulation equal to 6. But this allows us to show that these intermodulation product have a sufficient power level, even for input power of -10 dBm, that are able to build the quasi ultra wideband signal. But the simulation capabilities of any commercially available tools are limited with the number of intermodulation products. So we decided not to use the UHF frequencies as fundamental frequencies, but the common frequency, the frequency spacing as the fundamental frequency, and using the multitone represented as the higher harmonics of the fundamental frequency. This allows us to obtain the capabilities of very large simulations with a very large number of tones at the computational time of a very small, of a very reduced circuit. Here we have checked the idea, and as you can see on the right side, you can see the time domain waveforms at the output of the rectifier in case of a multi-sign periodic waveform and in case of a multi-sign quasi-periodic waveform. As you can see, when the content is more significant, the two plots are almost indistinguishable, but if you compare their computational time in the table on the left, you see that the periodic strategy, simulation strategy, allows us to include a much higher number of spectral lines at a very reduced computational time. Here are the results of our simulations for the 3rd, 4th, and 5th and 6th harmonics of our signal. And why we choose this? Because we are referring to the lower UWB European bandwidth. These are some results similar to the ones I have shown before for the 4th and the 5th harmonics by varying the number of tones and in this case also the frequency spacing. So you can see that we can rely on mainly on 2 degrees of freedom, the number of tones and the frequency spacing that can be exploited from the localization procedure that is based on a reference system like the one shown in this slide, where the UHF tag is powered by a multi-sign transmitter, and it is able to exchange to backscatter its quasi ultra wideband signal to 2 reference receivers, receiver A and receiver B. On board of them there is the signal processing algorithm to establish the localization of the tag. There are important degrees of freedom also in the localization algorithm that are mainly related to the duration of the observation time at the receiver sites and the frequency sampling. Also, there are the algorithm is able to filter out the waveform when noise and interference have a severe impact. And to establish the localization error. Here you can see some example of the results of the algorithm for different number of tones and time of observation. As expected, if time of observation is higher, the performance are better, and you can see here that we were able to reduce the error under the centimeter with a tag receiver distance as high as 12 meters. These are other results concerning a different combination of number of tones and frequency spacing, and we can conclude that if we are able to receive tones at the rectifier input that are with a larger frequency spacing, the performance of the localization algorithm based on the rectifier output UWB ports is much better. We have also realized the proof of concepts of this new harmonic tag. Here you see the performance of the measured performance in terms of power conversion efficiency of the rectifier, and the rectifier have been then connected to a setup that is shown in this slide, where the output UWB port of the tag is connected to a digital oscilloscopes with samplings at 10 microseconds of the backscattered signal, and these samples are used by the localization algorithm. Here are some representative results of the performance of the systems, where the power spectral density estimated by the entire design procedure and measured are compared. As you can see, significant mismatch is observed only for the highest harmonic, and we expect that is mainly due to the diode model that has been used. This shows some interesting features of the localization algorithm. When the tag is close, a rich mask including many spectral components can be considered in a plane wave, while where the tag is farther, the noise can corrupt the spectrum, so only few strong components are considered inside the signal processing algorithm in order to prevent from noise accumulation in the time direction of arrival estimator. Here we have some link budget where you can see that for different values of the received input power, and it can be concluded that our SNR values are obtained, enabling high accuracy localization when the tag is several meters far from the receiver. There are some other measured results where you can see that with a large bandwidth up to 12 and 16 meters with a time of observation of 500 microseconds, an error below 20 centimeters can be obtained by means of measured results. So I can come to conclude. We have proposed an effective solution for next generation UHF UWB autonomous tags that is able to simultaneously exploit multi-sign UHF excitations and to exploit the IM products generation in sort of for free, in order to backscatter a quasi ultra-wideband signal that can be successfully processed by our localization algorithm. So we can conclude that very promising results of circuit signal processing co-simulation have been proposed and also verified by measurements. So this concludes my talk, and I am more than happy to answer to your questions.